Okay, here's a part 2 of our lessons. So we're going to talk about differentiation and integration of power series. This is sometimes helpful in finding representation of functions in terms of power series. So let's say if you have a function and you can represent it as this power series in general form. So if you list a couple of terms, it is as follows. So let's say it has radius of convergence r. Then, so this is a theorem. Then the function is differentiable on, if you remember, this is your interval of convergence. Okay? If you remember the picture. This is a plus r, this is a minus r. Okay, then the function is differentiable on the interval of convergence. This is right here. And its derivative has a power series representation. Well, how do I get the derivative function power series representation? Well, you just look at the power series representation on the original function, then you take the derivative term by term. So if I take the derivative of c0, I get 0. If I take the derivative of c1 x minus a, this I have to apply power rule. So I have just c1, right? Because the derivative of x is 1, the derivative of minus a is 0. So I just get c1. And if I take the derivative here, I get, using power rule, I have to bring the power down. So I have 2c2 x minus a. Okay. Here you have to use chain rule. And you can do the same thing. The next term will be a c3 x minus a to the third. So bring the power 3 down. I have 3c3. Then subtract 1 from the power on the top. So I have x minus a to the second. Then chain rule tell me that now I take the derivative of x minus a, which is 1. So overall I have this expression. So in general, an n term, if you take the derivative, you would bring the power down. Then you subtract 1 to the power. So this is the power series representation for the derivative function of f. Okay? So in a similar fashion, you can do the same thing for the integral. So I can take the integral of each term using the power rule for integral. Well, the power rule for integral tell me that I need to add 1 to the power. So I have x minus a to the n plus 1, then divided by that new power, so I divide it by n plus 1. So if I list this series term by term, I have the following. Okay. And we know that if we take a definite integral, then we always add a plus c. So this is the power series representation for the integral of the function f. And this theorem also tells us that both of these power series representation for the derivative function and for the integral function has the same radius of convergence r as the original function. So this is a very helpful theorem to have because if I know how to represent a function f as a power series, then I automatically know how to represent its derivative function and its integral function as a power series. Okay. So let's see an example. So here's an example. I want to express this function as a power series. Then determine the radius of convergence. Well, if we would have done the way we did before, we would try to compare this function with the form 1 over 1 minus u. So we would try to translate this function into this form. Well, if you expand the denominator, you will get 1 minus 2x plus x squared. So I have three things in the bottom. Well, I can certainly let this part be my u, but then remember, once we write this in a power series, this u will be raised to a power. So I have to deal with a sum raised to many powers, which might be hard for me to deal with, because then I have to expand the sum as well. So maybe it'll be messy if we follow this way. So here's how we can apply the last theorem to tackle this problem. So I know that this series, okay, without the power second, I know that this is this series x to the n. So if I list a couple of terms, this is 1 plus x, etc. Now, if I differentiate on both sides, so I realize that there's a relation between these two series. If you not see it right away, then let's differentiate on both sides. So here I will use chain rule to differentiate. Here I'll just differentiate term by term using power rule. So I rewrite this as 1 minus x to the minus 1, taking the derivative of that. Or the derivative over here, you would just put the power down and then subtract 1 for the power. Because our first term, this is the 0 term, will be gone after we differentiate. This will become 0, right? The derivative of 1 is 0. So this series will start at 1 instead of 0, because this 0 term will be gone after you differentiate. So you can check it will match up if you differentiate term by term. The derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x, the derivative of x cubed is 3x squared, and so on. Okay. So if you take the derivative on this side, our chain rule tells us that I'll bring the minus 1 down, 1 minus x to the minus 2, so power rule. Then I have to times the derivative of the inside, which is 1 minus x. So this derivative will be minus 1. So I have minus 1 times minus 1 is positive 1. So I have 1 minus x to the minus second. I'll rewrite it in a cleaner way. So this is 1 over 1 minus x to the second. And we get that it's equal to this power series. So we get a power series representation of this function just by knowing what the power series representation for this function is. Okay. And by our theorem, this power series should have the same radius of convergence as this power series. And we know that the radius of convergence here is r is equal to 1. Right? This is convergent when x is less than 1, magnitude of x is less than 1. So here the radius of convergence is 1. So we should get the same radius of convergence here. Okay. Now let's look at another example. Find a Pell series representation for the function natural log of 1 plus x and its radius of convergence. Okay. So here we go. Natural log of 1 plus x, it looks nothing like the form 1 over 1 minus u, right? So there's no way that we can make it look something like this. However, we know that this natural log function of 1 plus x is somehow related to the function 1 over 1 plus x. If you, well, one is the derivative of the other. If you take the derivative of this, you will get this function. And this function, it looks like the form 1 over 1 minus u. So I can write this function as a power series. Then I just need to integrate this function or integrate that power series to get the power series representation for this. Okay, so that's my plan. Okay. So this function is, okay, so here I'll let u be minus x. Okay, so this become 1 minus u. So this is the series u to the n. So this is true as long as magnitude of u is less than 1. Then you replace u equal minus x in there. So we get minus 1 to the n, x to the n. So here's the power series representation for this. Now, this is the integral of this function. So now I just need to take the integral of both sides to get the power series representation for natural log of 1 plus x. The integral of this is the same thing as taking the integral of this power series. Okay. Okay. Well, if you're more comfortable, you can list term by term and then integrate that separately. So if I list term by term, starting at 0, I get 1 minus, at 1 I have minus 1 to the 1 is minus, x to the 1 is x. And then at 2, I go back to a plus, and here I have x squared, and so on. So if you integrate this, of course you get a plus c, and integral of this is x, integral or antiderivative of this is minus x squared over 2. This is positive x cubed over 3 minus x to the 4th over 4 plus dot dot dot. Okay. You can also just integrate or find the antiderivative for the general term. So this is the sum of so I have to add 1 to the power, right? Then I divide it by that same power, right? And our integral is only dependent on x, so this is minus 1 to the n. Okay, so we have a representation, power series representation for this function, which is what we mentioned, if you recall earlier in the lessons. Okay. So anytime you want to calculate natural log of a value, let's say the natural log of 3, now you would put x equal 2 in here. So you would calculate the sum of a bunch of fractions, minus 1 to the n, 2 to the n plus 1 over n plus 1, and depending on how precise you want the decimal expansion to be, you can just summing up to that. Okay. Well, one thing I need to talk about is we still have this plus c right here. So how do we find out what is this plus c? Well, to find out the plus c, I just need to let x equal to 1. Okay. Then my left-hand side becomes natural log of 1. Sorry, I'll just let x equal to 0. Then my left-hand side will be natural log of 1 plus 0. And this right-hand side would be 0 raised to some power plus c. Natural log of 1 is 0. 0 to some power 0, adding a bunch of 0 will be 0. So c is 0. Okay. So in general, this is the power series representation for the natural log of 1 plus x function. Okay. And this has the same radius of convergence as the one that we use to start with. 1 over 1 plus x. U is minus x. If you put minus x in here, it's the same thing as absolute value of x less than 1. So the radius of convergence here is 1. So the radius of convergence here is also 1. Okay, so I'll finish this section with showing this helpful relation, arctan of x, and the power series representation for arctan is as follows. Okay, so for arctan function, it has a relation with this following function. 1 over 1 plus x squared. If you remember, if you integrate this function, if you differentiate arctan, you get this function. So that means the integral of this function would give you arctan. This is a function where we can easily write the power series, which we already did at the previous example. So let me recall you, this is this power series. Okay. And the radius of convergence r is equal to 1 here. Okay. So I know that arctan of x is the integral of 1 over 1 plus x squared. Okay. So now I just need to integrate this power series to get the power series representation for arctan. Okay. And I won't list the term here, I will just do it generally for n. So here's the tip. These things are continuous. So you can switch the sum of an integral, integral of a sum is a sum of integral. Okay. So now I just need to differentiate term by term. I forgot to the end here. Okay, so I would add 1 to the power, then I would divide it by that. Okay, and I already integrate, so cancel my integral sign, and then I need to add a plus c. Now we need to determine what is this c is. So let's plug x equals 0. Okay. If you recall, arctan of 0 is 0. And this side, if I plug in 0, I have a sum of 0. So I have 0 equal plus c. Arctan of 0 is 0. So c is equal to 0. So we have a representation for arctan here. C is equal to 0. Okay, and this has the same radius of convergence as up here. R equal 1.